All right, here's another example of how to do problems in physics using work, energy, and power. And this time I'm going to show you a very interesting technique, something that you don't often see in any kind of textbook or learn in any kind of class. But from my experience, the students that I've worked with, they seem to really like this method. So take a look. The problem says a 20-kilogram box is pushed 50 meters up an incline, making an angle of 30 degrees with the horizontal, and having a coefficient of friction equal to 0.20. So now there's friction between the box and the incline. The box moves slowly and at a constant speed. We put that one in there so you realize that no energy was used to accelerate the box. Once you got it going, it's moving at a constant speed, so no energy or work required to make it go faster. And then it says, or it asks, how much work was required to do that? So the equation that I like to use is as follows. We have kind of a balancing of energy because energy is never destroyed or created. And so whatever energy you started with should equal the energy you end up with, unless energy was put in there by doing work on the system, or unless energy was lost due to like overcoming friction or anything like that. So the equation then becomes the following. The work put into the system, and of course work is force times distance, plus whatever potential energy you started with, so I'm going to call that whatever initial potential energy you had, and this little zero symbol there, that's a sub-naught symbol as we call it, means the initial energy, the one that you started with, plus any sort of kinetic energy that you started with initially, must equal the potential energy you end up with at the end, so we call it final potential energy, that's what F is for, plus the final kinetic energy, plus any heat lost by overcoming friction. So anytime you have to overcome friction or wind resistance or anything like that, you're going to have a term called heat lost. And usually heat loss is also expressed in terms of force times distance. In this case, the force may be the friction force times distance. All right, and so since they want us to know or figure out how much work was required, I believe we're looking for this portion of the equation. What is the amount of work done in this equation? Which means we have to account for everything else. So to understand a little bit better how to do this problem, let's make a little drawing here. Let's put it on the side so we stay out of the way of my equation. So here's the incline. The angle is 30 degrees. We have a box. Box is being pushed up by some force and moves a distance of 50 meters. So the displacement D is equal to 50 meters up the incline. The mass of the box is known. The mass is equal to 20 kilograms. And indeed, there's a coefficient of friction, mu equal to 0.20. I think that's all we know. Got the angle, we got everything. All right, so let's see how we do this problem. So first of all, since we're looking for this, we need to move everything else over to the other side. So we can write that the work done is equal to minus the potential energy initial, as we move it across the equal sign, minus the kinetic energy initial, plus the potential energy final, plus the kinetic energy final, plus any heat lost to overcome the friction between the box and the incline. Okay, now let's put in whatever we know here. Was there any initial potential energy? Well, if we assume that wherever the box started from, like from right there, we call that h equals 0. That's our reference height. That's where we started from, and we can arbitrarily call that 0. Doesn't matter if it's already partway up the incline. Let's just call that 0 height. So if it has 0 height, that means there's 0 potential energy, so we can say this is equal to 0. We can also assume that the box was not moving or barely moving. So if it's not moving, it doesn't have any kinetic energy, so no initial kinetic energy is 0. Now, potential energy final means at the end of the problem, when the box reaches this height, it has now gained some height right here, and let's call that height h. So it's gained potential energy, so we can write that it has gained mg times h, the weight times the height that it has gained. And then, since the final speed of the box is no different from the initial speed, because we say that the box moves very slow at constant speed, so there's no gain in speed, there's no gain in kinetic energy, so we can say that at the end, we can consider kinetic energy 0. And then finally, heat lost. Well, we lost some heat because we had to overcome some friction. And so therefore, the heat loss would be the work done to overcome the friction, and definition of work done is force times distance. So we can say that's equal to the friction force times the distance over which the box was moved. So now we have to find out what the friction force was equal to. So grabbing a pen of a different color, so we make some diagrams here. We can see that when we have the box have a weight mg. So there'll be a perpendicular component to the box, which we call mg cosine theta. And we have a horizontal component to the box, or I should say a component that's parallel, it's not horizontal, but parallel to the incline. So this is mg sine theta. Now, counteracting the weight component that's pushing the block into the incline, there will be an opposing component. Newton's third law requires that there is a normal force pushing back in the opposite direction with the equal amount of force of mg cosine theta. And this pen is not very bright anymore, so let's go ahead and throw that pen away. I'll grab the one that I know is working. So let me write that again. So this is the normal force is equal to mg times the cosine of theta, pushing back. And then by definition, the friction force is equal to the normal force times mu. And remember that it's always directed in the opposite direction of the motion of the block. Since the block is being pushed upward, we can then say that the friction force, let me use the blue pen, so the friction force, friction, is directed downward and is equal to the normal force times mu. And the normal force is equal to the mg cosine theta. So this is mg cosine theta times mu. So now we have a definition for the friction force. We can now plug that in here. So we can say that the work done is equal to, we have a bunch of zeros, so let's ignore those. We have the mgh plus the friction force, which we determined to be mg cosine theta times mu, and then we multiply that times d. Now we have to do one more thing. The height. We've gained h, but we don't know what h is. So we look at this triangle here. Then we realize that this triangle has the far side equal to h, and the hypotenuse is the displacement. So we can say that the height gained h is equal to the hypotenuse of the triangle d times the sine of the angle theta, because it's opposite to the angle. So we can say that's equal to d sine theta. We plug that in here for height. So we can say that the work done is equal to mg times the height, which is d sine theta, plus mg cosine theta mu times d. And now we have an equation that will allow us to calculate the work done to push the block up the incline. All we have to do now is plug in the numbers, although when you look at it, there's an m, a g, and a d. That's all the same in both terms, so let's factor that out. The work done is equal to mgd times the first term. We have a sine of theta left over, and the second term we have a cosine of theta times mu left over. Makes it a little bit easier to figure out the numbers. And then plugging in what these are equal to, the work done is equal to the mass, which is 20 kilograms, times g, which is 9.8 meters per second squared, times d, the displacement we said was 50 meters, and multiply the whole thing by the sine of 30 degrees, plus the cosine of 30 degrees, times mu, and mu is 0.2. And now we need a calculator. So we have 30 times the cosine times 0.2. Add that to the sine of 30, which is a half, so plus 0.5. And then we multiply that times 50, multiply times 9.8, multiply times 20. And we get the work done is equal to 6,597. 6,597. And of course, what are the units? Well, kilograms times meters per second squared, that's newtons. And multiply newtons times meters, that's Newton meters, which is joules. So that means the answer is in joules. And of course, I didn't round off to the correct number of significant figures, keeping in mind that everything was given to you with two significant figures. So properly, we should write the answer in two significant figures. So if we want to do that correctly, we write the work done is equal to 6.6 times 10 to the 3 joules to maintain the correct number of significant figures if that's what we want to do. So that's how you work out a problem like that. And remember, the nice equation here is really applicable to many more, and I'll show you some examples of how to use that on some additional physics problems like that.